Okay, let's have a look at this question here. So the first part is fairly standard, De Morgan's theorem for sine 3 theta. So we have cos theta plus I sine cubed, cos theta plus I sine theta cubed. That should equal cos 3 theta plus I sine 3 theta. So we can get the fact then that I'll expand it first. That becomes cos cubed theta plus 3 cos squared theta I sine theta plus 3 cos theta I squared sine squared theta plus I cubed sine cubed theta is equal to cos 3 theta plus I sine 3 theta. The imaginary parts I'm interested in. It's the real parts I'm not, which is this guy here and this guy here and this guy here. So just looking at the imaginary parts, I sine 3 theta then will equal actually I didn't need to write the I, but oh well. I 3 cos squared theta sine theta, and I cubed is minus I sine cubed theta. So if we just get rid of those i's, I shouldn't have written them down in the first place. We have to do something about the cos squared. So this would be 1 minus sine squared theta sine theta minus sine cubed theta. So that's going to be 3 sine theta minus 3 sine cubed theta minus sine cubed theta. So the answer is 3 sine theta minus 4 sine cubed theta. So that's De Morgan's theorem for sine 3 theta. And the second part is the proof of De Morgan's theorem. And I've not actually seen it done this way before. When I've seen the proof of De Morgan's theorem before, it was using a Taylor series. But from thinking about it, I can see why this is a little bit nicer, because you don't need to rely on Taylor series here. So our first thing we have to do is show that this is a constant, and we can do that by differentiating. So we'll use the product rule. So first we differentiate ei theta, so that becomes I ei theta, and then we keep this cos theta minus I sine theta, and then we'll have plus ei theta, and then we differentiate the inside. Cos becomes minus sine theta, and then minus I sine becomes minus I cos theta. So what simplification can we do? Let's multiply this out. I ei theta cos theta plus I by I is I squared, which is minus 1, so that's plus ei theta sine theta minus ei theta sine theta minus ei theta times I times cos theta, and that's equal to 0, which then if you differentiate and you get 0, that implies that ei theta times cos theta minus I sine theta equals a constant, since the derivative of a constant is 0, and theta is the variable here. Which is x usually, but theta now in this line here. So we've shown that it's a constant. Therefore, it's true for all thetas. So regardless of the theta, it's this constant. I mean, that's what it means to be constant. It'll be the same value regardless of the theta here. So that implies we can just choose theta equals 0. So then the constant will equal e power 0 cos 0 minus I sine 0. Well, sine 0 is 0, cos 0 is 1, e0 is 1. So you're just left with 1, which is a success. So now we have to arrive at the formula here, ei theta equals cos theta plus I sine theta, and we can use this fact. We can use the fact now that ei theta cos theta minus I sine theta is equal to 1. So that means ei theta is equal to 1 over cos theta minus I sine theta. I multiply above and below by the conjugate, cos theta plus I sine theta over cos theta plus I sine theta. So on the top, I'll get cos theta plus I sine theta, and on the bottom, I'll get cos squared theta plus sine squared theta when I expand, which of course is equal to 1. So I'm left with just cos theta plus I sine theta. So I've shown that ei theta is equal to cos theta plus I sine theta. That theta's up a little bit high. It looks like it's a power of the I. I think that's just a font error. It's not this, it's this for sure. So that's just whatever way it was typed, the theta just looks like it's raised a little bit too much. So yeah, it is definitely I times theta there. Okay, so that was an interesting little question there, and that's that one taken care of.